Good morning, everybody. Today it's gonna be our first lab session. So, well, I see you all have your laptops, which is good. You can open your editor. I'm gonna use Visual Studio Code. You can use whatever editor you like, doesn't matter. I suggest that you use a Python editor, whatever that is. Visual Studio Code does work for Python as well as many other languages. The first file we're going to work with is this file here, which is in the folder reactive control, TSID, and the file name is x0ur5 joint space control. So you should all open this one. I'll give you a moment to do it. You can start taking a look at it in the meantime. So this file contains an implementation of QP-based control. Unfortunately, not everything is implemented in Python because we are relying on a library which is called TSID, which stands for Task Space Inverse Dynamics. It's a library that I developed together with other people, and it's written in C++, but it comes with Python bindings, which means that we can actually use it from Python without looking at the C++ code, which makes it much more user-friendly for teaching. So I suggest we start by taking a look at the code together. So I can give you a quick introduction, quick overview, and then we're actually going to spend most of the time playing with this code more than writing anything. So the script is already completely written and working. If you run it, you should see a robot doing something and then some plots appearing. But what I really would like you to get today is an understanding of what's going on and gaining some insights by playing with the parameters of the script to change the motion that we are asking the robot to do, to change the problem formulation, the control problem, and to see how the robot behavior changes. So let's start. These are just flags that I typically define at the beginning of every script, which you can set to 0 or 1 to enable or disable the different plots, which are done at the very end of the script. Then URDF files, do you know what URDF files are? No? Nobody knows? URDF, like what's written here, URDF. Okay, so these are basically XML files that contain the description of a robot, both in terms of geometry, so number of links, the distance between the links, the degrees of freedom, and in terms of dynamics. So the mass of every link, the center of mass, and the inertia matrix of every link. So basically, that's everything you need to know for computing kinematics and dynamics of a robot. And it's a standard file format that is very widespread in robotics. And so we rely on that format for basically acquiring all the information on the robot.
No, that we don't have that line of code. Yeah.
Did you download the latest version of the library?
Yeah.
So what could have gone wrong is that you're relying on Docker, I guess,
Yeah.
and you did not update the Arc repository using git pull. You missed that step. If you miss that step, then you have an old version of the repository which does not contain that line.
Thank you.
You're welcome. And by the way, my advice in the instruction was not to do that, because if you're relying on the version of the Arc repository which is inside Docker, everything you're going to change in that file is going to be lost once you leave the Docker. So I don't think that's what you want. Okay, so what was written in the instruction is use a shared folder between the Docker image and your host OS, and download the Arc repository inside that folder. And if you do that, well, you have the new version of the repository because you just download it.
I have
The shared folder,
yeah.
and you should download the Arc repository inside that folder. So that's when you modify the file, it remains after you quit the Docker image. Okay, so basically this function here that we are calling is finding in your OS the URDF file of this robot. The robot is called UR, which stands for Universal Robot. It's a robot brand that we're going to use for many of our tests. We also have those robots upstairs in the lab. That's why I picked them. And then we create this robot wrapper. This is an object that we're going to use a lot. It's basically our interface towards the robot model. So it's a class that contains all the functions that we need for computing the robot Jacobian, the end effector, position, the mass matrix, the bias forces. So every kinematics and dynamics quantity, we can compute it using this robot wrapper. Here it's a bit confusing that we have two robot wrappers. One is called robot and the other is called robot simu. That's because in general, you may want to use a different robot model for doing simulation with respect to the one that you're using for doing control. Because maybe you want to simulate what would happen if you didn't have an exact model of the robot, but you had a slightly different model of the robot. You want to evaluate the robustness of your control method. So in general, these two models could be different. So we use two different models. In practice, in this example, they're going to be the same. And then we also have a robot simulator. This one is implemented in Python, so if you want, you can go inside and take a look. It's not necessary, but if you're curious, you can. And the robot simulator basically relies on the robot model for doing simulation. And it contains also all the code for the visualization of the robot in the viewer. So maybe before we go any further, we can just run the script to see what happens. So to run the script, I suggest you to open a terminal. You go in the correct folder, which is reactive control TSID. Here you have this file x0 ur5 joint space control, and you simply run it with the command Python and then name of the file. So when you do that, you should see a viewer which opens up in your browser. The robot moves. And then you see some plots. Here are the plots of the joint torques. These are the joint accelerations. You have 6 of them because the robot has 6 joints. Here we have the joint velocities. And finally, we have the joint positions. Of course, we haven't understood yet what the script does exactly, but just to check that everything is working. If you can see that, it means your software is well configured. Inside the viewer, you can move the camera position like this. If you use the left mouse button, you can rotate around the origin. If you use the right mouse button, you can translate the vertical and lateral directions. And with the scroll, you can zoom in and zoom out. So you have 3 ways of moving inside the viewer. And you typically need to adjust a bit the viewpoint so that you see what you want to see. And every time you're going to run the script, it's going to open a new window inside your browser with a new viewer. And the previous one is disconnected. Okay, so actually you can just close it. Are some of you able to see that? Can you raise your hand so that just I understand more or less how many people? Oh, very few. So I guess everybody else is having troubles with the software. I was hoping to have a slightly lighter, greater percentage of success. Okay, well, later I'm gonna give you some time to play with the script, and I'm gonna help whoever needs help. Let's now move on with reading the script. So what's happening here is that we are creating an object which is the main object that we use to define the control problem. And it's called inverse dynamics formulation ax force. It's a mouthful. Ax force means that inside the QP problem, we use as decision variables the joint accelerations and the joint forces. So we have removed the joint torques from the decision variables. That's a strategy that we use for making the problem smaller and more efficient to solve, but it doesn't change anything in terms of the math. So this object is going to be the one that we use to basically interact with the controller. Then we define a vector Q0 that contains the initial joint angles, and V0 contains the initial joint velocities. The velocities are simply set to 0 because, well, usually your robot starts from 0 velocity. And the initial joint angles, we take it from the configuration file, which is called conf. So conf, you can see above, it's actually just an alias for the file called x0ur5conf, which is a file in the same folder, which I suggest you also to open. I've opened it here. And this is a file containing all the hyperparameters you can play with. So most of the time today, we're going to actually change values that are inside the configuration file, not inside the main script. I typically try to separate the main script from all the hyperparameters of the script. I think it makes it a bit cleaner. So among all the hyperparameters, you have the initial configuration of the robot, which is nothing more than a six-dimensional vector containing the joint angles for all the joints. So this is the initial configuration that I've chosen. You can change it if you want. Okay, then what I do here is that I need to define the tasks and the constraints inside my QP-base controller. This script defines a very basic instance of QP-base controller. So it contains one single task, which is called posture task, which is nothing more than a joint space control task. So we are simply trying to track a reference trajectory in joint space. So there is a class for defining such a task, which is task joint posture. We need to define the value of the proportional gain, Kp, the derivative gain, Kd. The proportional gain is defined in the configuration file. You can see it's conf.kp posture. It's a scalar, so to transform it into a vector, I multiply it times a vector of ones of size 6. So robot.nv is, in this case, 6. It's a number of degrees of freedom. And the value of Kp posture, I can check it in the configuration file. By default is 1, which is going to be quite small. The derivative gain, very often we don't directly specify it, but we simply set it to 2 the square root of the proportional gain, because that typically works quite well. For the derivative, yeah. This comes from linear control theory. There is a reason why 2 square root of the proportional gain is a good value for the derivative gain. So if you've taken some linear control theory class, you might have seen that. It's the so-called critically damped value. If you don't like it, you can also replace this with any ad hoc value you want to have for the derivative gain. Then once we have defined the posture task, we add it to the formulation with this add motion task method. And when we add a task to the formulation, we need to specify the weight for that task. Because if you remember, when you have multiple tasks, you basically sum all the cost function together with different weights. In this case, the weight doesn't matter because you have only one task. So it doesn't matter if the weight is 1 or 1000 or 10 to the minus 3. It's gonna be the same. And you must also specify whether this task must be considered as a constraint or as a cost. And you have this flag, which you can set to 0 or 1. If you set it to 1, it's a cost. If you set it to 0, it's a constraint. In this case, I've decided to set it as a cost. And this very last value here, which I set to 0, it's the transition time. So in case you want to add or remove task while the robot is operating, you might want to have a transition time in which the task is introduced in a smooth way, so that you don't have an abrupt change of the control problem, which may result in discontinuities. Well, in this case, it doesn't matter because we are just starting, so we don't need any transition. So you can set the last value to 0. Then every task needs a reference to follow. In this case, we are using this trajectory Euclidean constant. This is going to be simply a constant reference value. It's not going to be constant in practice because we are going to change this reference value at every time step, but it's constant from the viewpoint of this object. So this object doesn't have an internal dynamic. So when you call the method compute next, it's always going to give you the same value that you set. But then you can change the value. So once we have created this posture task, so this reference posture, we pass it to the task using the method setReference. Then besides the task, we also add some inequality constraints. So we have this other object, which is called task joint bounds, which is designed to have to specify bounds in joint space. So you can have acceleration bounds, velocity bounds, position bounds. In this case, we only set the velocity bounds with this method here, set velocity bounds. We specify Vmin, Vmax. Vmin and Vmax actually come from the model, which contains the velocity limits for all the joints. But then we scale these limits by this factor, Vmax scaling, which is specified in the configuration file. And by default, you will see this is set to 0.4. You can change it, of course. I set it to 0.4 to make the problem a bit challenging, because if you don't scale it, then it's just too high and you never hit it in this example. And basically that's it. So we only have these two things in our control problem. We have a joint task and joint velocity limits. Yes?
This scale of 0.4 is only when the vector is reaching the bound.
So this is a scale that's applied to the joint velocity limit. So I'm reducing the joint velocity limits to 40% of the real value.
Only when I'm reaching the
No, this is applied all the time. Yeah, it's a constant, always there limit. So the controller is always going to try to maintain the joint velocities within those bounds. I add the joint bound task to the formulation, and here I specify the flag to constraint level. So this is going to be a constraint, not a cost, which is what we wanted. Then I need to create a QP solver for solving the QP problem. This is a solver I decided to use. And then basically I start preparing all the vectors for my simulation. So these are going to be the NumPy arrays that contain all the quantities that I want to log during my simulation. So I will log the joint torques, tau, the joint angles, q, the joint velocities, v, the joint accelerations, dv, and then the reference values for joint angles, velocities, accelerations, the desired joint accelerations, which I guess you don't remember what they are. So I'm going to write it here. The desired accelerations are the reference acceleration plus kp times qref minus q plus kd times vref minus v. Just as a reminder. And then here I have these quantities, amplitude, phase, and frequency, which are going to define the reference joint trajectory, which is going to be simply a sinusoid. But I can specify what amplitude, what phase, and what frequency this sinusoid should have. Everything is specified in the configuration file. So we can actually go there and take a look. So the amplitudes are 0 for the last 3 joints. So the last 3 joints should simply not move. But then I have some amplitude for the first 3, 0.2, 0.3, 0.4. Consider that these are in radians. So 1 radian is roughly 60 degrees. So 0.2 is roughly, well, you make the math. But I mean, it's not super small. It's not 0.2 degrees, which would be a tiny motion. I mean, this is relatively large. And in terms of frequencies, we are ranging between 0.3 and 1. Okay, and then basically we start with the for loop, which implements the simulation. So at every iteration of the for loop, we do a few things. First, we compute the reference motion, which is, as I told you, a sinusoid. And I not only need the reference joint angles, I also need the reference joint velocities and accelerations. So I computed the derivative. Well, the derivative of a cosine the derivative of a sine is a cosine, and the derivative of a cosine is minus sine. So this is what these three lines are doing. Once I have the reference motion, I pass it to my posture task with these 4 lines here. I need to use this object sample posture to pass these 3 values to the posture task. And then basically this method here computes, transform my problem specification into a QP problem. So it does a so-called transcription from robotics problem to optimization problem. And then once I have the QP problem, I pass it to the solver, which gives me a solution. Every time you're using an optimization solver inside a control loop, you want to check the status of the solver, because it might happen that the solver was not able to find a solution. So you need to know that. Well, in this case, we are doing simulation, so we don't care if it breaks. But when you're on a real system, that's super important. So we check if the status is different from 0, it means the QP problem could not be solved. So in this case, we simply print this message and we stop the simulation. Otherwise, we recover from the solution the joint torques, the joint accelerations. We also recover the desired accelerations just for logging. And then we simulate the system for one time step. So we call the simulate method of the simulator, which takes as input the joint torques and the time step for the simulation. Time step, I think, is 2 milliseconds. Yeah, 2 milliseconds. So pretty fast. Then we log the value of the joint angles and the joint velocities taken from the simulation. We increment the time. And then we display the robot in the viewer. To make the thing a bit faster, we don't update the viewer every 2 milliseconds. Anyway, our eyes are too slow to see that. Our eyes, I think, are able to see updates at 20, 30 Hertz. So it wouldn't make sense to update the viewer at 500 Hertz. We are just wasting computation time. So I only update the viewer every few steps of simulation. And then these last 2 lines are to make sure that we are not running faster than real time. Because if you just run this code without this sleep, then it's going to be faster than real time. And so what you see in the viewer is too fast for you to really see. So I check how much time have I spent for this whole computation here from the beginning of the 4 to the end of the 4. And then if the time that I've spent is smaller than my time step, I sleep for the remaining amount of time. So that's this loop basically runs in real time and not faster. Of course, if your computer is very slow, it may happen that this loop is slower than real time. In that case, there's nothing you can do. Okay, so this loop repeats for a certain number of time steps, which in this case is going to be 2000. So we have 2000 iterations. Every iteration is simulating 2 milliseconds. So in total, we should have 4 seconds of simulation. You can make that longer or shorter by changing these values here. And after that, it's just plots. So plotting the joint angles, plotting the joint velocities, plotting the joint accelerations, and plotting the joint torques. So not very interesting code to look at. I suggest you, however, to take some time to get familiar even with this code for plotting, because you're going to need it later. When you're going to do the assignments and the final projects, you will need to plot stuff, so you will need to understand and replicate this code. Okay, so now we have a decent understanding of what's going on inside the script, so we can go back to the terminal and we can run it and analyze a bit the plots. Okay, so let's see. Here we have the joint torques. Is there anything interesting you see?
Yeah, beats and like discontinuities.
Yeah, we have discontinuities. Inside the plots, you can zoom things in all directions. When you zoom the time axis, it scales the time axis on the 6 of them, which is, I think, a nice feature. So when you move, you see horizontally, they're all aligned. So the time axis is actually shared between the 6 plots. And we can see indeed that there are some moments like this one, for instance, where we have a discontinuity in the joint torques. So we're going from -7 to +3, roughly. Any idea why that happens? Why? Well, you don't know exactly because we haven't looked at the other plots yet, but why in theory that could happen? It could be a reasonable thing for the controller to do.
Maybe because the velocity is faster at some point. But...
Yeah, we have velocity limits in the controller. So if you think about it, it's reasonable that when we hit a velocity limit, so we reach the maximum value or the minimum value, there is a discontinuity in the behavior of the controller, because there is something that has flipped, basically. Before we were within the limits and now we are at the boundary. So there is a discrete change in the situation, which might justify a discontinuity in the joint torques. Well, now we need to validate this hypothesis, and I think we can do it by looking at the joint velocity plot, which is this one. And if we zoom in here, indeed, we can see that roughly at 0.34, you can see when I put my mouse on a point in the plot, in the bottom right corner, I have the coordinates of that point. That's also useful to know. I guess it's very small for you to read, but it's 0.34. And we can check. Yeah, that's exactly the same moment where we have the discontinuity in the joint torques. So the hypothesis was correct. It's reaching the limits in the joint velocities creates a discontinuity in the joint torques, which is reasonable. So what the controller has to do is that when you're at the limit of the joint velocity for one specific joint, in this case, that's actually joint 0, the first one, it means that I can no longer accelerate that joint in that direction. In this case, it's a negative direction. So it means that I need to go from an acceleration that is negative because the velocity is decreasing to an acceleration that is 0. So there is a discontinuity in the acceleration, which we can also check because we also have the acceleration plots here. And look at that. We went from a negative acceleration to 0 acceleration on that joint. And since the joint torques are proportional to the accelerations, well, if you have a discontinuity in the acceleration, you're going to see that as well in the joint torques. So actually, this plot here of the acceleration is probably the most interesting to look at because it doesn't show us only the real accelerations and the reference accelerations, but we have a third quantity, which are the desired accelerations. Do you remember? So the desired are the reference plus the PD feedback terms. Okay. So if you have a tracking error, the desired and the reference are going to be different. If your tracking is perfect in this moment, then desired and reference are going to be just the same. So in this case, we can see that desired and reference, which are the green and the orange, are different because when we start, we have a tracking error. And we can see that for a while, the real accelerations, so Q double dot, which is the blue line, is exactly equal to the desired acceleration, which makes sense because that's actually what we are asking the controller to do. The cost function, if you remember, is the square difference between the real accelerations, Q double dot, and the desired accelerations, Q double dot des. So for the first phase of the motion, these two quantities are equal, at least for this joint, but actually also for the other joints. If you take a look around, you can see they're all equal for all joints. And then here at this point, which is the point when we reach the joint velocity limit, this is no longer the case because the desired acceleration remains negative, is -5 roughly, but the real acceleration becomes 0 because otherwise we would have violated the joint velocity limit. Okay, so this is what's happening inside the controller. So the joint acceleration for that joint remains 0 until the desired acceleration, Q double dot des, becomes positive again. And then at that point, it can keep tracking the desired value until this other moment here, where the same thing happens. And well, of course, the reason is always the same because probably we have reached again the joint velocity limit, but now on the other side.
Just explain briefly what is the difference between the reference and the desired?
That's what I wrote here because I know that's a bit tricky to wrap your mind around. It's this. So the desired is equal to the reference plus the feedback.
So the desired is basically
the desired is the value that you use in the cost function. It's your target value for the cost function. The reference is simply the second derivative of the reference joint angles. So this value here doesn't depend on how the robot is moving. It's a fixed value that you know in advance. Whereas this value here depends on the feedback, because you see there is Q and V in this equation. So it depends on how the controller is doing. If the controller is lagging behind, then the desired accelerations are gonna increase. Whereas if the controller is keeping track with the reference, then the desired are gonna be just basically equal to the reference.
The reference would always be.
Yeah, if everything goes perfectly, desire and reference are gonna be the same. Yeah, that's because when I start, I already have an error. I have an error here because my joint position is not equal to the reference at the beginning for this joint. And even for the other joints, which actually start from the reference position, they don't start from the correct velocity. You can see it here. Because the robot starts with 0 velocities, but actually the reference velocity at the beginning is non-zero. So since we have this initial tracking error, then we are in this situation where desired and reference are not the same. Well, that's up to you. But yeah, it's a good practice to start with a 0 reference velocity, I agree. I've carried out several experiments with a non-zero initial reference velocity in my life, so it's not such a crazy thing to do. It's not ideal, but for sinusoids are very convenient reference movements for testing your controller, and it happens that the sinusoid starts with a non-zero velocity because the cosine of 0 is 1. So this is something that can happen in practice. But even if we started with a perfect initial state, you would still accumulate errors along the way. In simulations, those errors would be very small unless you introduce some noise, some uncertainties, some model errors. But in practice, on a real robots, they wouldn't be. Okay, so yeah, just to finish what I was saying before, these are the velocities, and we can see that we are hitting the lower limit here, and then we actually are also hitting the upper bound here, even if for a much smaller fraction of time. And we keep doing that for a while, if I remember correctly how this goes. Oh no, we just do it the first 2 times, the first 2 oscillations, we hit the velocity limit, and then we are quite good. No, well, okay, no, we hit it again, but only on the upper bound. We keep hitting the upper bound until the end, but not the lower bound. Okay, so in terms of joint position tracking, we can see that this is what happens. And this is actually what you mostly care about. You care about tracking the position reference. It's not doing a great job, I would say. It's slowly getting there, but especially for joint 0, it's getting there way slower than I would like. Because in 4 seconds of simulation, we are still far off the reference motion. For joint 1, situation is a bit better, but still not completely satisfying. I mean, in 4 seconds, I would expect the controller to catch up with the reference. It shouldn't take so long. So I think now we can go back to the script and play a bit with the hyperparameters to try to improve the tracking. Yeah.
In joint 3, 4, and 5, there are many no smoothness. It's like the arm is shaking.
Yeah, good point. You should take care. You should take a look at the scale of the plots when you look at them. So here the scale is 10 to the minus 16 or 17, which means that this motion that you're seeing here is actually 0. So if I change the scale of these 3 plots to be the same scale of the other 3, you would see just a flat line at 0. So it seems that they're shaking, but actually they're not. They're really standing still. So don't be fooled by the scale. Okay, so maybe I give you a few minutes to play a bit with the script. Focus on the configuration file. Here you have a few hyperparameters that you can play with. Try to make the motion tracking performance better. Try to make the robots catch up with the reference before the 4 seconds of simulation are done. And in the meantime, maybe I can help some of you that have software issues. So we have been mostly focusing on fixing software installation issues today, which is how usually the first lab session goes. So no surprises there. Has any of you managed also to play a bit with the code? Okay. Did you manage to improve the tracking?
Yeah, for example, I simply increase the proportional gain as your previous advice.
Yeah.
And
how much?
I tried with 10 and it was good enough.
Yeah.
In 20, there was also the velocity is not limited, so does not reach the limit.
Let me try. So I also increased it to 10. Let's see how it goes. Joint torques, we don't care so much. Joint accelerations, joint velocities, maybe later. Let's take a look at the joint angles. And yeah, so already switching from gain of 1 to a gain of 10 changed a lot the tracking. And we can see after a couple of seconds, basically, we were able to catch up with the reference. And after that point, we basically stay on top of it. It's not surprising, we are in simulation, we have a perfect robot model, no uncertainties, no noise. So everything works quite well. We are still hitting the joint velocity bounds here, but not the lower bound, we only hit the upper bound. And for a very small amount of time. So this was an easy fix, actually. Now we can try to make the problem a bit more challenging. So for instance, we could try to increase the frequency of the movement to make it faster, or increase the amplitude of the movement. For instance, what if we make the frequency, I don't know, 1.2 instead of 1.0? we can see that it's struggling. So it catches up, but it struggles with the upper peak of the sinusoid. My guess is probably that's related to the velocity limit. Yeah. You can clearly see that the reference velocity is beyond the maximum velocity of the joint. So clearly the robot cannot track it perfectly. But we are asking the robot to do something that's physically impossible. But that's actually good. I mean, that's exactly what we want the controller to do. If the user is asking the robot to do something that's unfeasible, well, the controller shouldn't do it. It should satisfy the physical limits of the machine first, and then, if possible, achieve the task that the user is asking. So basically, we are asking too much. So we should go back. Then other things we can play with are, for instance, introducing Coulomb friction in the simulator. You have a flag here, which is simulate Coulomb friction in the same configuration file. It's set to 0 by default, but if you set it to 1, you're basically enabling Coulomb friction simulation. You should also modify the tau Coulomb max, which defines how much is the Coulomb friction. And this is specified as a percentage of the maximum torque of that joint. I would say a reasonable value might be 5%. So if a joint can produce at most 100 Newton meters, the Coulomb friction on that joint is 5 Newton meters. I think that's realistic. And we can check now how that affects the tracking. Let's start as usual with the positions. It affects the tracking a lot. So now the robot is not able at all to track the reference motion. And now, I mean, I went back to the frequency of 1. So before introducing Coulomb friction, this motion was totally achievable. Now with Coulomb friction, it doesn't work. What do we do?
Why Q2 is completely 0?
It's because of Coulomb friction. I mean, you could say, okay, why aren't then the others 0? It depends. It happens that the Coulomb friction at this joint is so large that the torque that the controller is asking at this joint is not sufficient to overcome the Coulomb friction. Since this is a smaller joint, it's, I guess this is the elbow joint probably. The inertia that you have after the elbow is smaller than the inertia that you see at the shoulder. So the torque that you need to accelerate the elbow is smaller. And this torque happens to be smaller than the Coulomb friction torque. And that's why it doesn't move at all. So that's something that happens also in reality. When you have friction at the joint, maybe you start the controller and the robot just doesn't move because you're not overcoming the Coulomb friction. So how do we fix this? Yeah, it's a common pattern. Oh, look at that. No, okay, no, the scale is 10 to the minus 14. So we have this high frequency oscillations, but they're tiny, so they don't matter. So the gain was 10. Well, let's make it simple. We set it to 100. That should do it. Not completely. I mean, joint 0 is okay-ish. Joint 1 struggling a bit more, but it seems to catch up towards the end. Joint 2 still not good. And now look, also joint 3, which before was moving, but with a very, very small scale. We had like 10 to the minus 16 here. Now instead it's moving significantly while it shouldn't, because the reference is actually to stay fixed at 0. And this is an effect, again, of Coulomb friction, which is counterintuitive in a certain sense, because Coulomb friction should only make the joint move less, not move more. So why is this happening? Yeah, the phenomenon is clearly stick slip. Here we have a sticking phase and then it's slipping, sticking, slipping. Okay. But actually what we are asking the robot to do is not move that joint. So if the controller is trying not to move the joint and we have on top of that friction, which should help sticking, maintaining the joint still, why is it moving? It's because of the dynamic coupling between the joints. When you generate torque at your shoulder, you're actually generating an acceleration also at the elbow, at the wrist, at all the joints of the chain. There is dynamic coupling. So even if the controller is not trying to move this joint, since it's trying to move the other joints, and there is this friction which is unmodeled, so the controller doesn't know it's there, this could result also in undesired motion in other joints. So probably I would say this is the coupling between joint 2 and joint 3. And yeah, we are still not very satisfied with the motion of joint 2. So we know what to do, right? We can try to make it track better by increasing the gains. Where are my gains here? Let's try 300, because maybe 1000 is a bit too high. Okay, at least it's starting to look like a sinusoid. Even joint 1 improved a bit, I would say, with respect to before. Still, we have this undesired motion of joint 3, but that's part of the game. Also, joint 4 started moving a bit, but here the scale is still pretty small, so we don't care. And here, this one is roughly half a degree of motion, so small. I think we can tolerate that. I'm more concerned with the tracking error of joint 2, because this is still a quite large tracking error. It's 0.1 radians, I would say, which is roughly 6 degrees. So this is not negligible. We can push it. We can increase the gains even more. Let's see when it breaks, if it breaks. mean, being in simulation, the breaking point for high gains is actually much further than it would be on a real system. So like gains of 1000, apparently they work. And now the tracking error is actually quite small. So this is quite satisfying. However, we can check if this would still be the case having a slower controller. So now we are running the controller every 2 milliseconds. What if we make it run every 5 milliseconds? Still pretty fast. It's 200 Hertz, but less fast than before. Is it still gonna work? I don't know. Let's try. Yes, still working. I also made the simulation time longer by increasing the time step because I didn't modify the number of time steps. So now it's simulating for 10 seconds instead of 5 seconds. But we don't mind. You can try to make it even slower. It's not uncommon to have controllers that run at 100 Hertz, for instance. Let me decrease the number of simulation steps in this case, otherwise it becomes way too long. Still fine. So actually in this case, friction might be helping us also to stabilize the system. We can try to disable friction and see if the controller is still working well. Yes, still working well. You can see now that the motion in the viewer is not smooth anymore. That's because when I change the time step, I should also change this value here, which defines how often I update the viewer. Now I'm updating the viewer every 20 time steps. And when the time step was 2 milliseconds, that was fine. But now that my time step is 10 milliseconds, actually, I should make this smaller. So maybe I can make this 4 instead of 20. So if I rerun it now, I should see the viewer, yeah, move smoothly. Doesn't change anything in the plots, it's just the viewer. Okay. Let's see what else we can play with. I would like to play with the simulation accuracy because I still would like to make the controller break. Okay, so you see that the simulate method, besides taking the control inputs, so the joint torques and the time step, it has also another parameter, which is NDT. And NDT, you can see it as a parameter that allows you to tune the accuracy of the simulator. By default, it's 1, and that's the minimum. If you increase it, you're making the simulation more precise because you're increasing the number of simulation steps of inner simulation steps per controller time step. And the more steps the simulation takes, and the more it's precise. So we can try to make this value higher. So here I'm going to add ndt equal 10. So for every, actually 5 is fine, should be enough. For every controller loop, the simulation is gonna compute 5 simulation steps inside. So the simulation steps are gonna be 5 times finer than the controller steps. This should increase the accuracy of the simulation, make it more realistic. Okay, it's not changing anything. I wanted to break it, but apparently I cannot. Okay. Anything else we can play with? Let me check. I think there's not much more than we can do with this example. It's pretty basic. So I suggest we move on to the next example, which is a bit more complex. So, and that's going to be the file x1 ur5 task space control, and the corresponding configuration file, which is x1 ur5 reaching conf. So this is a file. It's pretty similar to the previous one, but as the name suggests, now instead of controlling the robot in joint space, we are going to control it in task space. And the task space in this case is the Cartesian space of the end effector. So there is a key difference, is that now instead of defining all the problem inside the script, I'm relying on an external class, which is called TSID manipulator, which contains a definition of the problem using the TSID library. And here there is just everything else, which is very similar to what we had before. So computation of the reference trajectory, which in this case it's in Cartesian space, calling the controller, logging quantities, doing plots. That's it. Let's open this file. If you're on Visual Studio Code or any other Python editor, probably if you control-click on the name of a class, it should automatically open the file. Makes it faster to navigate. So this is the class I was talking about. So as the comment here says, this contains a definition for a TSID formulation for a robot manipulator, which contains an end effector task for controlling the position of the end effector, postural task for controlling the joints, torque limits, which we didn't have before, and position and velocity limits of the joints. So before we only had the velocity limits. Now we also have the position limits. So here the code should be pretty similar to what we have seen before. The main difference is that after creating the joint posture task, so for controlling the joint angles, we have a second task that we create and add to the formulation, which is called task SE3 equality, which may be not very intuitive, I guess, for you. Do you know what SE3 is? SE3? It's typically written SE, and then the 3 in parentheses, the special Euclidean group. It's basically the space in which position and orientations are defined. So if you want to define the configuration of a rigid body in space, like this water bottle, well, that's defined by a position and an orientation. Okay, that's in SE3. It's not an Euclidean space because while the position is in an Euclidean space, which is R3, the orientation is not, because that's a manifold. So you need to take care about that. That's very related to the discussion we had a couple of weeks ago about representing orientation, the fact that you can use quaternions, rotation matrices, angle axes or Euler angles, and you have minimal representation which suffer from singularities, and so on and so forth. So this is a task for controlling basically position and orientation of a body of your robot. However, in practice here, we are going to use it just to control the position of the end effector. So when you create such a task, you need to define what is the name of the frame of the robot that you want to control. And that's in the configuration file, which is here. And you can see the name is this one, and the effector fixed joint. So inside the URDF file, which is a file containing the description of the robot, every body of the robot has a name. And so you need to identify which body of the robot you want to control by using that name. In this case, the very last body has this name, which is called end effector fixed joint. Then you set the proportional gain, the derivative gain, and you also need to set the task mask. Task mask, again defined here. This is a 6-dimensional vector which defines which subspace of the end effector pose you want to control. The first 3 elements correspond to X, Y, and Z directions, so position. The last 3 elements corresponds to the 3 orientations, basically. So roll PTO, basically. In this case, I've set the first 3 to 1 and the last 3 to 0s because I only want to control the position and not the orientation of the end effector. If you set everything to 1, then you're controlling both position and orientation of the end effector. And you can choose whatever combination of these you want to use. We have a weight, of course, for the end effector task, which we're going to set to be higher than the weight for the posture task. In particular, by default, you can see here that the end effector task has a weight of 1, while the joint posture task has a weight of 10 to the minus 3. So it's way, way less important than the end effector task. Then we have the joint torque limits, joint velocity limits. So actually we don't have the joint position limits. We could try to add them later. And nothing more. So let's simply try to run the script and see what happens. Python x1 ur5 task space control. Okay, now you can see that there are these 2 spheres in the simulator, that one of them represents the reference motion, the other one represents the real position of the end effector, identifying the points that we are controlling. Now here, when we are doing the plots, of course, we're going to be interested in looking at what's going on at the end effector, but also we want to keep an eye on what's going on at the joint level. So we have the torques, the joint velocities, and then we have the end effector position and velocity in 3D. So that's the end effector trajectory, X, Y, and Z. Z is by convention the vertical direction. X is the forward direction. Y is the lateral direction. That's typically how it's done. So X is tracking pretty well. Also Z is tracking pretty well. In the Y direction, we are seeing a bit more deviations, but actually that's mainly an artifact of the scale, because the scale here is smaller than for the other two axes. So here this deviation corresponds to 2 millimeters. So it's pretty small. Still noticeable because, I mean, most of the time we don't have any deviation, and here we actually have. And this moment corresponds actually to the peak of the reference in the X direction. So it's not by accident that this happens at this moment. So we can try, as usual, to understand why that happens. This is a plot of the end effector velocities, but that's not super interesting. I'd rather look at what happens in joint space. And we can see that there are some interesting moments, like here. We are hitting the joint velocity limits on joint 2 and also on joint 4 and also on joint 3 more than once. So we have all these joint velocity saturations happening. This could explain why we have some deviations from the reference motion. And we can also take a look at the torque limits. And here we are saturating the torques, but for very short amounts of time, it seems. Like at the very beginning of the motion, we have a saturation, both in joint 4 and joint 3. And maybe here as well. Yeah. Couple of times also for joint 1. But I would say that it's mostly coming from the joint velocity limits, the deviations. How can we test that? Well, we can go to the configuration file and we can increase the joint velocity limits, because now we were setting them at 40% of the real value for this robot. We can try to increase it to, I don't know, 60%, and we can repeat the test. You can also notice that at some points the robot is going in singularity because the elbow is completely stretched. That also might explain why it's not tracking perfectly. So joint velocities, well, we are still saturating a few times, but much less than we did before. That's an improvement. And also in terms of tracking of the end effector trajectory, we still have some tracking errors, but they are much smaller than they were before. So here we are in the sub-millimeter errors. You can see it by looking at the scale. So the whole plot here is less than 1 millimeter in height. So yeah, the problem was coming from the joint velocity limits. That being said, I mean, if those were our real joint velocity limits, there was nothing we could do to fix it. Here we just tested the hypothesis by increases the joint limits, but you cannot do that on a real system. What we can do now is that we can play with the reference trajectory, because now we are simply having this reference which is very easy to follow, but we can try to make it a bit harder, like by increasing the amplitude in the x direction. So we could see that already the reference motion was making the robot go in singularity by stretching out completely. If now we increase the amplitude, well, we can imagine that it's not going to be able to reach it, but it should still be able to do something. Let's see. Okay, you can see that now the red ball really goes way beyond where the robot is able to reach. And that is clearly visible in the tracking. In the x direction, now we have some large error here. This is about 10 centimeters of tracking error, which again is reasonable. We are asking the robot to track a trajectory which is outside its workspace, so it cannot do it. What we want is not a perfect tracking, but we want to maintain a good behavior of the system despite the non-perfect tracking. So that's going to be our focus. So let's take a look at what happens in terms of joint velocities. Do we like that? Of course, no. Otherwise, I wouldn't have asked. Especially, I don't like this. So in half a second, this joint is going from minimum to maximum to minimum to maximum to almost minimum velocity. That's not something that you want on a real robot. Of course, in simulation, nobody complains, but on a real system, this wouldn't go well. So when you see these high frequency oscillations, typically it's a sign that you might want to tune your controller a bit better before testing it on the real system. Question is, how do we fix this? Because it's not violating any limits. The joint velocity limits are satisfied. What are our options?
Probably decreasing the gain.
Decreasing the gains. Can try that. So the end effector gain was 100. We set it to 10. Oh yeah, that's much better. I mean, it's still a bit too wild for my personal taste. I wouldn't run this on the robot because this transition is very fast. But at least now it's one transition and not 5 of them in a row. So it's definitely an improvement over what we had before. Of course, here in simulation, since now we don't have any unmodeled effect, we can decrease the gains basically as much as we want and still achieve a good tracking. On the real system, you're more bounded to do that. Because if you increase the gain too small, then the tracking deteriorates a lot. I think there is still a lot we can do to play with this script. So on Monday, we can keep going on with the lab session, playing with the script. You're more than welcome to play with it during the weekend. especially if you're still having some software issues with installation, I strongly advise you to fix them as soon as possible. If you cannot do it on your own, I'm here for you. Send me an email or just stop me after class because I want you to have the software running as soon as possible. Okay, also because in 1 or 2 weeks, I'm gonna give you the first assignment. So you will need to have the software working to complete the assignment. Okay. So I'll see you on Monday. Oh, you have a question?
Yeah, do these oscillations from minimum maximum happen when the singularities happen? Like when the
Yeah, it corresponds to the moment where the robot goes in singularity. Yeah, exactly. Yeah. Okay, see you on Monday.